last class we started error correction. So, you saw this example about Alice trying to send a message to Bob over a channel that corrupts up to 10% of the bits, and so Alice has to encode. Okay, so, the result of the encoding is called a code word. Code word is sent over the channel. The channel may corrupt some of the bits, which means it may flip some of the bits 0 to 1, 1 to 0, and then Bob gets y prime. Y code word y becomes y prime, and the question Bob has to now solve is from y prime he has to find y and then x. That was the original message. So, what we want from the code is that the distance should be large, so that more errors can be handled. Length of the code word should be small, so that the channel is not expensive, and obviously you want all the algorithms to be efficient, which means randomized polynomial time. So, first we will look at the existential state. What is the best distance and the length that you can hope for? That is given by Gilbert-Varshamov bound. So, the theorem says that or this lemma states that there is a code which will basically give every string in 0 1 to the n a random m bit code word, where the distance will be delta, which you can pick to be any constant between 0 and half. So, let us show this. So, we will basically just have to randomly pick the images, the code words. Okay. So, pick y1 to y2 to the n at random, and define the code to be x mapped to the xth y. Okay, so, 2 raised to n strings are mapped to 2 raised to n strings, but these images are longer, that is m bits. Now, let us look at the distance between yx and yx prime, or yi and yj, right. So, for every ij pair different, we are interested in this delta yi yj being less than delta, this event. So, over the choices that E makes, what is the probability that fractional Hamming distance between yi yj is less than delta, right? This will be the bad event. So, this bad event, what is the probability? This is this probability is less than equal to, you can think of yi as already fixed. So, I mean yi, this image, so you are picking both yi and yj randomly, but you can assume yi to be fixed and then yj is what you are picking. So, what are the good yj's over all possible yj's, right? So, number of yj's which are close to yi. So, number of delta m places in yj divided by number of possible yj's. Or I should say maybe y, this is, let us say this is yi. So, if you want yj close to yi, then you basically have to pick delta m locations in yi and just flip them, right. So, every this subset choice will give you a bad yj and divided by the total number of yj's possible. So, which is what? Which is equal to, so you have m locations in yi, so you get m choose delta m, let us call it m choose I, and I goes from 0 to delta m, right. That many ways you can change yi to get yj, and total number of yj's is 2 raised to m. Now, this basically this binomial sum is what you have to estimate. So, you can see that m choose delta m, which is the largest summoned here, that will be much smaller than 2 raised to m, right. So, that is given by Stirling's approximation. So, you can actually write it like 0.01 times 2 raised to mh delta and 2 raised to m in the denominator. So, this is really what you get. You get that the binomial sum is 2 raised to is much smaller than 2 raised to m, and this exponent is h delta given by the Shannon's entropy function. Okay, this is really coming from Stirling's approximation. Okay, so you can look this proof up of Stirling's approximation. It basically gives you a very good asymptotic bound for m factorial, and then using that you can get bounds for binomial numbers, and then you can also get bounds on sum of binomials. So, if you sum up to delta m these binomial numbers, then you get a value smaller than 2 raised to m h delta. Okay, so, if you take delta to be half, then this is square root of 2 raised to m, 2 raised to m by 2, that is the point. So, that is the probability that if you randomly pick yi, yj, they will be close. Okay, the distance will be smaller than delta, but we are interested in all the pairs ij, right. What is the probability for that? So, that you can now deduce. So, probability over E that there is a pair which is very close. So, you go over all the pairs, number of pairs is smaller than 2 raised to 2n. So, let us also throw that in. So, what you will get is 2n minus m 1 minus h delta. So, it has grown larger by a factor of 2 raised to 2n, but still if you take m to be quite large, appropriately large, then this fraction is very small, this probability is very small. In fact, at this point you should see what m is. We have fixed in the lemma m to be 2n by 1 minus h delta. So, you already get that this is 0.01. Okay, and that means that probability for all I different from j, the distance is large. Okay, this probability is more than 99%. So, if you randomly choose your images, then these strings are far away, further away than fractional Hamming distance delta, right. And what m did you require? M you required is 2n over 1 minus h delta. So, it is order n. So, that finishes the proof. So, now you know where you stand. This code certainly exists. It exists for any delta smaller than half, but actually here you can see what will happen if you take delta to be exactly half. Okay, so, in this calculation, if you take delta to be half, then you have to estimate m choose m by 2. So, what is m choose m by 2? Let us also do that. So, for delta equal to half, you will get sigma m choose delta m okay. This expression you will get to be around 2 raised to m over square root m. Okay, in other words, if you look at the probability expression this, then you get 1 over root m. So, 1 over root m will be multiplied by 2 raised to 2n. So, you will need m to be 2 raised to n. Required in the proof. So, instead of m being order n, now it has become 2 raised to order n, it has become exponential. Okay, so, if you want to reach delta equal to half, it is possible, but then you will need an exponentially large m and exponentially longer code word. Now, what happens when delta is greater than half? Then you can show that E cannot exist. Okay, this you can show simply by looking at the space 0 1 to the n or 0 1 to the m, and there just by triangle inequality you will get this. Okay, so, delta greater than half is not possible, delta equal to half is possible, but exponentially large. Delta less than half, by a random choice, E exists. And so, what you learn is that this code E allows unique decoding up to errors delta by 2. And delta is close to half, so that is around 1/4. Okay, so, this existential code E tells you that theoretically or information theoretically unique decoding is possible, even if there is 25% error. Okay, so, Alice sent this message or this code word to Bob, and 25% of the string was corrupted. Still Bob can recover the original message, right. So, this is an amazing thing. The only part missing is, can this be done efficiently? Can encoding, decoding be done in poly n time? Okay, so, encoding can be done in this existential proof. It can be done in 2 raised to n time, because it basically goes through all the strings in 0 1 to the n. So, can you make it poly n time, and also randomized is allowed? So, can you solve this problem in randomized polynomial time? Okay. So, we will study four explicit codes. And as will happen, these will be linear codes, okay, which means that if you take two messages and add them, their code words will also add to give the new code words. These will be linear codes, they will be efficient, and they will have good distance and many other properties, amazing decoding properties. So these have, let's enumerate them. So Walsh Hadamard, this will have distance maximum, which is half. Then Reed-Solomon, this will have distance smaller than half, but it will be very efficient. Third is Reed-Muller. So this will be similar to Reed-Solomon. It will be, Reed-Solomon basically works with univariate polynomials, this will work with multivariate. And finally, combining two codes, which are called concatenated codes. So the property will be, these will also be efficient. Reed-Solomon is not a binary code, it will use finite fields. Reed-Muller as well will use finite fields. Concatenated codes will be our final choice. These will have all the properties. These will be binary and these will be efficient. Distance will be constant, less than half. We'll strengthen the notion of decoding gradually. We'll first start with unique, how to decode uniquely, which we will do in Reed-Solomon efficiently and in Walsh Hadamard inefficiently. From unique we'll move to local decoding. Local will be that you will need to query very few places your corrupted code word. And finally, local list decoding. Which is non-unique. So finally, we want local list decoder. Okay, so local means that query very few places in the corrupted code word and still get a bit of the original message. And list will mean that, in fact, the options of, I mean, you are in a regime where there may not be a unique message X. So then you want to output a list of messages. But obviously the list has to be small. So we'll do this gradually. This will take several lectures. So let us start with Walsh Hadamard. That is the simplest, although inefficient. It has to be inefficient because we are demanding delta half. After that, we'll look at more and more advanced coding techniques. So this is quite old. This is from 1940s, Walsh Hadamard. So remember, you want delta half, so you expect the length to be exponentially blown up, and what you can do is just take your message x and take all possible inner product with the space. So, space has 2 to the n strings. For every string you take inner product with x, and that is how you get 2 raised to n bits. That is your code word. So, for 2 strings in the space 0 1 to the n, define this inner product as sigma xi yi mod 2, okay, this bit, the natural inner product, and then define the WH code, Walsh Hadamard code. So, n is stretched to m is 2 raised to n, and the way you stretch it is for any x, you map it to a string z, where the yth location of z is inner product of x with y. Okay, so this is the definition of your inner product between 2 strings, and the code is just doing an inner product for every it basically takes inner product of x with every possible location y, and there are 2 raised to n locations. So, it is a 2 raised to n length string. You can also think of this as projections of x, all possible projections. Modulo 2. Okay, so, you project inner product is also like projection, but this is mod 2. So, there are 2 raised to n projections possible, and you project in every direction. That is Walsh Hadamard code. What good is this map? So, what we will show is that Walsh Hadamard is an error correcting code with distance half. So, we have to show that for different x and y, the code words WHX and WHY, they are very far apart. Okay, we have to calculate their distance. In other words, the 2 strings WHX and WHY, they will be different in half of the locations or more. So, first you note that WH x plus y, this plus you can do coordinate wise addition mod 2, right, 2 strings x and y. So, if you sum and then take Walsh Hadamard, it is the same as adding Walsh Hadamard x with WHY. Where plus is coordinate wise sum. Right, coordinate wise sum mod 2 also means just the parity coordinate wise. So, this is easy to see because x will go to z and y will go to z prime, but when you look at a location, in that location you are taking only inner product. So, inner product is linear. Okay, since this inner product is linear on the location string, this property holds true, which means that if you look at the weight of this vector, weight means number of non-zero entries. Number of non-zero coordinates. This will be WHX plus WHY weight, and so if you look at a location, it is just the sum mod 2, right. So, only when the two coordinates are different, the two bits are different, will they give you 1. If they are same, it will give you 0. It is just parity. So, it is the same as the difference between these two strings. And since it is fractional Hamming distance, you multiply it by m. Okay, so, this is delta times m, delta between these two strings. So, the distance between two strings gives you the weight of WH image of the sum. So, now if x plus y is not 0, then what you get is, note that then x plus y, a non-zero vector basically is orthogonal to, it can be orthogonal to how many vectors? At most half of the vectors in the space, right. So, x plus y is orthogonal, not just at most half, exactly half. So, this is orthogonal to exactly half of the vectors in 0 1 to the n, right. This you think about. So, a non-zero vector is orthogonal to exactly half of the space, and it is not orthogonal to half of the space. So, using that property, you know that weight of this Walsh Hadamard x plus y is half. Weight of Walsh Hadamard, because Walsh Hadamard vector is nothing but collection of these inner products. Half of them is 0, half of them is non-zero. So, you get weight to be m by 2, which means that delta is half. For x not equal to y. Okay, so, for different strings, the WH image, these two code words, they differ in exactly half of the places. Okay, that was your claim of lemma 1. Lemma 1, you had to show that Walsh Hadamard is an error correcting code with distance half, and we have shown that indeed if you look at the images, the code words, they are far away. and moreover it is a linear code word, but it is very long, right. So, we want shorter code words. So, WH achieves maximum distance, but this M is exponential. So, now to get shorter code, we have to do something else. To get a shorter code, we will look at finite fields. So, we will use more algebra. Okay, so, finite fields. Other than F2. Okay, so F2, you can say that Walsh Hadamard worked with the finite field F2, field with 2 elements. It did addition mod 2, but inspired by this, we will now move to finite fields, and we will get the first brilliant code, which is the Reed-Solomon code. Okay, this is from 1960s. So, Reed-Solomon code, we will move to finite fields, and the idea is to view the input string as a polynomial, as a function. View the input string as defining a function, which is basically a polynomial, and then you evaluate that polynomial, and evaluations are then sent as the code word. As a polynomial, and consider its evaluations. In a finite field. Okay, this is the basic idea. Instead of thinking of a string as a vector in hypercube 0 1 to the n, now you think of the string as a polynomial, and this polynomial, when you will evaluate, get many evaluations, that is your code word. So, let us define it formally. So, let F be a field n is smaller than m and m is smaller than the field size. Okay, we will take a finite field. So, n smaller than m and m smaller than the field size. Now, the RS code is the following map. Okay, it will instead of a string, it will actually take a point in f to the n. And it will give a bigger point in f to the m, it will stretch. So, that will be, so let us say point was a0 to an minus 1 that you started with. What this will give you out is z0 to zm minus 1, where zj is supposed to be the evaluation of a polynomial defined by a0 to an minus 1. So that is the polynomial AI so the polynomial is sigma AI times Fj is an element to the I. The polynomial is basically these coefficients a0 to an minus 1. Okay, the polynomial coefficients are a0 to an minus 1, and then you evaluate at the jth point. For the jth element, Fj in F. Okay, so that's the RS code. RS code is mapping a point a0 to an minus 1 by defining a polynomial and then evaluating it at Fj. So we can write that down. So the polynomial is sigma ai x to the I. Okay, this is the polynomial that the given point a0 to an minus 1 defines, and you just evaluate this polynomial at many field elements, exactly m field elements. Now again notice that this is a linear code, because if you take 2 points and look at the RS code words, when you sum the 2 points again coordinate wise and in the finite field, then the code words will also add up, right. This is because the 2 polynomials you can add. You can add the 2 polynomials and then evaluate, or you can separately evaluate and add. So this is again a linear code, and the property was, so what is the distance of this? So RS is an error correcting code of distance So if you take m to be more than double that of n, we are claiming that the distance of RS is half. Actually, you should be careful here. The distance notion here is for the finite field alphabet, right? This is not binary anymore. So let's remember that. So the alphabet is now not 0, 1, but the field elements F. And in that alphabet, if you look at the distance, so RSX and RSY, how far they are in terms of the coordinates, compare them in the field, then a lot of them are different. Okay, that is what this lemma is saying. Let's prove this. So again, like in lemma 1 we did, right? So RS of A minus B, take a point A in F to the n, take a point B, take the difference coordinate wise. This is equal to RSA minus RSB. For coordinate wise sums. Let's do it properly. So, again A is a point in f to the n, B is a point in f to the n, A minus B means that you coordinate wise subtract. And when you do that, you can see that the polynomial that you are getting, you can subtract the polynomials, and so evaluation of the polynomial and then subtracting, or subtracting the polynomials and then evaluating will give you the same value, which means that again weight so if you look at the number of entries in LHS that are non-zero, right, that will be given by the number of places where RSA and RSB differ, because the places where they are equal, the difference will be 0. This is again similar to what we did before. Which is the fractional Hamming distance, but now in this alphabet, field alphabet, between RSA and RSB, and since it is fractional, you multiply by the number of coordinates, which is m. And again, if A minus B is non-zero, A and B are different, then RSA minus B is a set of m evaluations of the non-zero polynomial AI minus BI, right, coordinate wise difference, then x to the I less than n, this polynomial. The degree of this polynomial is less than n, you can assume n minus 1. Now, how many evaluations of this can be 0, right? This maximum n minus 1 evaluations are 0. So, remaining evaluations are non-zero. So, at most n minus 1 evaluations vanish, which means that if you look at the distance, times m. So, this number of coordinates is at least m minus the ones that are vanishing, which is at most n minus 1, right, which means that the distance is at least 1 minus n minus 1 by m, which is what we wanted to show. However, if you look at the binary distance, so for binary distance you have to actually look at the coordinates in binary. Now, when you look at field alphabet, two field elements are different, but that only means that when you look at the binary representation, one bit is different, right. It is possible that just one bit is different, not all the bits. So, what you will get is this m minus n minus 1, these many coordinates are different, but the number of coordinates is not m, it is now you have to multiply by the field element in the binary alphabet. So, that will give you log factor. So, actually this distance is this becomes smaller then. Okay, if you look at the binary distance, it is much smaller, but if you look at the non-binary distance, that is very close to 1. If as the bigger you pick m, the closer to 1 it is. Okay, so this is not really contradicting Gilbert-Varshamov bound, because that was for binary alphabet. Reed-Solomon is for non-binary alphabet. That's the notion of distance here. So, this is delta for F alphabet. Okay. So, we have seen that Reed-Solomon is a linear error correcting code and distance is close to 1, which means it is separating the strings very far away. Let us move to the next code. So, for now we are only looking at the distance in encoding and distance, right. Decoding we will see later. Decoding is always complicated. So, Reed-Muller code is similar time. What is the idea of this? Idea is similar to Reed-Solomon code. Again, view the string as a polynomial and consider evaluations, but multivariate polynomial. And consider evaluations. Okay, so this will be the multivariate generalization, but the expressions will now become more complicated. So, let us go through the definition again. So, let F be a finite field L, D are numbers and D is smaller than the field size. L will basically be the number of variables, D will be the total degree. Now, the Reed-Muller code is this map, which will take L variate D degree polynomial, or that many, I mean, so that L variate D degree polynomial can be described by how many coefficients. So, that number is L plus D choose D, right. L plus D choose D field elements define a L variate D degree polynomial. This polynomial you evaluate in all possible ways, which means how many evaluations? F to the L. That maps every L variate D degree polynomial P to all evaluations. In the space F to the L. Okay, for every point in the space F to the L, you evaluate this P and hence you will get f to the L many coordinates, that is your code word. Okay. So, explicitly also we can write this. Rm will map, so coefficients you are given is coefficient vector is C I bar. I bar is basically L tuple coordinate summing up to D. So, I bar you can think of as the exponent vector. And what should you map this to? So, Rm is mapping this to this polynomial evaluation. So, this is I1 IL less than equal to D. Exponent vector sum is less than equal to D for all x1 to xl. So, you start with coefficients and you end up with evaluations of this polynomial P. Okay. So, I hope this clears up what the Rm map is doing. So, first observation is let us compare this with the Reed-Solomon definition and Walsh Hadamard. So, both the codes that we saw before. In Walsh Hadamard you can think of D equal to 1. So, Rm with D equal to 1, if you make degree to be 1, then you are basically looking at a linear polynomial and if you also fix the finite field to be F2, then what you are doing is given these L bit string, you are just evaluating all these linear, you are evaluating this linear polynomial which L bit string defines, and hence you are just computing the inner product in all possible ways, all projections. So, you actually get the WH code. Now, to get Reed-Solomon you just fix L equal to 1, right, that is natural. If you take a univariate version of Rm code, then this map is just the definition of Reed-Solomon. Right. So, this is why Reed-Muller code is important. It is actually a uniform generalization of both these important codes that you saw. Walsh Hadamard with delta, which is a binary code with distance half, and Reed-Solomon, which is a non-binary code with distance almost 1. Okay. And yeah, what is the distance calculation for Rm code? So, Reed-Muller is an error correcting code with distance one minus d by the size of the finite field. First of all, it is a linear code. Why is it linear? Well, for the simple reason that when you look at two coefficient vectors, the difference of them coordinate wise means that the polynomials also you are taking the difference, and then if you evaluate, you will get the same value as if you had first evaluated and then taking the difference, right. So, the same reason as you saw before, Reed-Muller is a linear code, and we will show the distance calculation now. This again is a non-binary distance. So, again if you look at the weight of Reed-Muller image of difference of two strings A and B, right, like before, this will be the weight of, since it is linear, RMA minus RMB, which means that you have to consider those locations where RMA and RMB differ. So, you go to the distance. Times M. What is M? So, M is field size raised to L, F to the L, right. Okay. So, now you have to compute the weight of RMA minus B, which means in how many places is it non-zero, right, like we did for Reed-Solomon code. So, if A minus B is non-zero, different coefficient vectors, then this polynomial that you will look at, then this polynomial has how many zeros? So, here you have to use this multivariate bound on the zeros of multivariates, which we call polynomial identity lemma. By that you will notice that you get d by f. Right, by the polynomial identity lemma. Which means that this fraction may vanish, but the remaining will not, and hence you get delta to be at least 1 minus d over f. Okay. So, that finishes the proof of distance. Next time we will start concatenated code.